Okay, class. So once again, in the last class, we discussed MATLAB assignment number 2, and I talked with you about permuted LU factorization and how that relates to MATLAB assignment number 2. The idea is that computers, to reduce round-off error, well, no. Let me ask you this. In the first column here, in the first column of this matrix that you see, you have the numbers 1, 8, and 4. As humans, what number would we use as a pivot to get zeros in the first column? What number would we use? The 1, the 8, or the 4? We would use the 1. Very good, very good. But a program like MATLAB, in order to get that matrix in echelon form, we would use a 1 as a pivot to get zeros in the first column, in the first 2 bottom spots. But MATLAB would use partial pivoting. With partial pivoting, what number is used as a pivot to produce zeros in the other 2 spots? What number is used as a pivot? The 1, the 8, or the 4? All right, what number would be used as a pivot? Olivia thinks 4. Does anyone think something else? Haley thinks 8. All right, and I appreciate both answers. Abby thinks, okay, so I'm actually glad I'm going over this. I'm getting some different answers, and so I'm glad I'm going over this. Partial pivoting is going to take the largest number in the column and use that as the pivot. That's what partial pivoting is. In section 1.2, they mention that as a, hold on, I believe it's a numerical note. Yeah, numerical note that comes after example 3. So, the reason is because partial pivoting will help reduce round-off error. Okay, for instance, if you're solving a system of equations. Now, I'm going to show you that, but of course, to do partial pivoting, where do we want the 8 to be? The 8 is in the second row. Where do we want the 8 to be? If we're going to use 8 as our pivot for the first column, Eleanor, we want 8 to be in the first row. And so that means we have to interchange the first and second rows. So if we're going to allow partial pivoting, then if we're going to allow partial pivoting to get an LU factorization of a matrix, then we have to allow row interchanges. And when we allow row interchanges, we do what's called permuted LU factorization. And we talked about that in the last class. And there's a video, there's a recording on that. I recorded our discussion. But I want to show you why computers want to use the largest number in the column to use as a pivot. That's what I want to do. And so on that note, let me bring up this little handout here. And this handout actually was given to me a number of years ago by a student who was taking a numerical analysis class. And it says Gaussian elimination at the top, but that, of course, that's just doing row operations to get the matrix in reduced echelon form. It's just a synonym. Okay, and so we're going to go right here at the bottom, and like you had said, if you double click on the document, it'll make it larger, or there's controls at the top left hand corner. So let's look at this very simple system. Okay, very simple system here. Okay, two equations, two unknowns. And so we have 0.000025x1 plus 1x2 equals 1. And then we have 1x1 plus 1x2 equals 2. Now I can tell you that the exact solution to this system of this little system of equations is x1 equals 40,000 divided by 39,999, and x2 equals 39,998 divided by 39,999. And the way I got that was I took this decimal, okay, the 25, hold on, the 0.000025, I took that decimal and I converted it to a fraction, and I did the row operations, and this is the exact solution. Now, this solution, x1, x2 solution, what is it pretty close to? What are those fractions pretty close to? Yeah, that's right, Samantha. 1, 1. So the exact solution is pretty close to the solution x1 equals 1 and x2 equals 1. Okay, just keep that in mind. Just keep that in mind. All right, are there any questions so far? All right, all right. So what we want to do, and again, we're going to go to the next page, okay? And we're being asked what result is obtained if Gaussian elimination is applied to this linear system using floating point arithmetic. So that means means using decimals, okay? And there are comments here in the border of this document, and those were written by the student who gave me this document. So you don't need to worry about those. Just kind of focus on what I'm not saying they're wrong or anything, but just kind of focus on what I'm telling you about. So to make pencil and pen computation easy, we're going to round to 4 significant digit decimal arithmetic. 4 significant digit decimal arithmetic. That means the result of every add, subtract, multiply, and divide, which is what computers do, right? Floating point operations, what do you call it? Flops. Okay, but everything we do, we're going to round to the nearest 4 decimals. So, all right, let's say that this system, they say consider what happens if the exchange step is not used. So exchange step means a row interchange. That's what that means, row interchange. Okay, so what they do is, all right, you want to reduce well, if I go back here, you know, what do you want to get here in this spot? What do you want to get right there, where that 1 is in this system of equations? If you're going to do row operations and get it, and you want a 0 there. So what do you have to multiply the first row by? What do you have to multiply the first row by to get? So of course the 0.00025 would be your pivot. That's the smallest number in the first column. That's the smallest number. You're used to using small numbers. Ben's right. You'd have to multiply that decimal by negative 40,000, and so you'd be multiplying the first equation, the first row, by negative 40,000, and adding that result to the second row. And if you do that, you're going to get a 0 where that 1 is, which is what you're used to, right? So here again, we're using here we are using the small, we're not doing an interchange. We're not doing a row interchange. We're strictly going to use the smallest number in the first column, which is 0.00025, multiplied by negative 40,000. We're going to use that as the pivot, the 0.000025, smallest number in the first column, okay, like we're used to doing. Okay, so if we multiply that decimal by negative 40,000, we will get a 0 here. You know, we will get a 0 there in that spot, which is what we wanted. Okay, and hold on here. And it says here we're going to get a negative 40,000 here in this spot. Now let's stop for a moment, because negative 40,000 times 1, if we go back here, negative 40,000 times 1 plus that one there equals what? What's negative 40,000 times 1 plus this one? In other words, I'm going to take negative 40,000 times this one, good, and add it to this one here, and I get negative 39,999. But we are using 4 significant digit decimal arithmetic. So negative 39,999 would be rounded to what? What would negative 39,999 be rounded to if we're using 4 significant digits? How many significant digits are here in that number? There are 5, right? So we have to round that. We can't have 5 significant digits. We need 4. So very good, very good. I know people are chatting. Eleanor and Benjamin are chatting in the chat window, and thank you for all the responses so far. So this is going to get rounded to negative 40,000. So negative 39,999 becomes negative 40,000. Okay, so far, are there any questions? That's a rounding error, Okay, we used a small pivot, and we have a rounding error. Okay. Okay, now let's look at this other piece here. If we take 1 and multiply it by negative 40,000, and then add it to 2, okay, because we're taking negative 40,000 times the first row and adding that to the second row. What's negative 40,000 plus 2? Well, negative 40,000 plus 2 is negative 39,000, good, marvelous, 998. But what is the computer going to round that to? If the computer is using 4 significant digits, what would this be rounded to? Negative 40,000. Good, marvelous. And so, hence, this is why, and they mention this in the, in the paragraph above, but I'm just sort of verbally stating it. There's that negative 40,000 right there. Okay. And so now we have the system in echelon form, okay, and it's quite easy to solve for it. The second equation would give you x2 equals 1, and if x2 equals 1, well, all right, well, hold on. So x2 equals 1, and by the first equation, x1, if we were to solve the first equation by x1 would equal 1, hold on here, one moment here. Yeah, so the first equation here, the first equation to solve for x1, we would subtract x2 to the right side, so we'd have 1 minus 1x2, and then we divide by 0.000025, and that's going to give us this. But x2 is equal to 1 from the first equation, and so if we substitute 1 for x2, we get a 0. So using four significant digits, rounding to 4 significant digits, and we know computers round. Now they go a lot more in terms of digits, but hey, you know, look at what happened here. We rounded to 4 significant digits. Did we get a good answer? Is you know, x1 equals 1 and x2 equals 0? Is that a good answer? Is that answer close to the exact answer? What was the exact answer to the system of equations close to? If you go back here, here's the exact solution right here. What's the exact answer close to? X1 is close to what? X2 is close to what number? Good, Benjamin. X1's close to 1 and x2's close to 1. Well, by not having a row interchange, okay, not allowing that, and using the smallest number in the first column as a pivot, when we solve the system, we got x1 equals 1. Okay, so that's okay. But then we get x2 equals 0. Do we like that? Are we happy? Are we happy with this answer? This answer that our computer, quote, computer gave us using decimal point, floating point arithmetic. Are we happy with this answer? No, we don't like this answer. So, you know, I'll put like trying to draw this. I'll put a sad face there. Well, that's kind of an angry face, but you know what I mean. We're not happy. I don't know. I can't draw a happy face too well, class. Okay, but does that look like a happy face? I don't know. That looks like an angry face, right? But it's a sad face. So we don't like this answer. We really don't like it. Okay. So okay. Well, let's try now to interchange the equations. So if you go back here to the equations, here they are, and you interchange the first row and second row, then this is going to be your system. This is where we include, they call it the exchange step. We did a row interchange. And so now we're going to use the 1 as a pivot, okay, to produce a 0 where the 0.000025 decimal is. But 1 is the largest number in the first column. It's the largest number. So this is partial pivoting that we're doing here. So we're going to multiply to produce a 0 in that spot right there. What do we have to multiply the 1 by? If I want a 0 in this spot here, and I'm going to use the 1 as a pivot, what decimal do I multiply the 1 by? Okay, Benjamin, right, -1 over 40,000 or -0.000025. Oh, but when we do that, okay, we get a 0 here. All right, and that's fine. I think everybody's good with that. Okay, but why did we get a 1 here? Why did we get a 1 here? Well, what is 1? what is 1 minus 0.000025? That's 0.999975, but that rounds to 1. That rounds to 1.0000. Why can't we use the 0.999975? Why are we restricted from using that? Pretend we're a computer. Why are we restricted from using that as a computer? How many significant digits is the computer using? 4. So how many significant digits are in 0.999975? Good, Marvelous. Good, Eleanor. How many significant digits in that decimal? 6. Can't use 6 decimals, so we got to round it. Okay, and if we round it, it rounds to 1.0000. Similarly, if we take for this number here, so the 1 here stayed a 1, and the 1 here also is going to stay a 1, because 1 minus 2 times 0.000025 is 0.99995, and that rounds to 1. Okay, so now let's see what we get. All right, so based on this system here of equations, based on this system, okay, well, x2 equals 1, and x1 will equal 2 minus x2, but with x2 being equal to 1, we get x1 equals 1. So are we happier with this result here? Are we happier with this result? Did we get a better, is our solution, I mean, the solution x1 equals 1, x2 equals 1 is an approximation to the actual solution, but is it a better approximation? Did we do a lot better? Did we do a lot better here when we did. Thank you, Olivia. And so you see, the idea is that when you use the larger number in a column, if you use the largest number as the pivot, if you use the largest number in the column as a pivot, it reduces round-off error. Okay, and the approximate solution will be better. And that's why we use partial pivoting. That's why computer programs like MATLAB use partial pivoting when they do their row reduction. And if you have a matrix that is 1,000 rows and 1,000 columns, okay, and you're doing, you're using a computer to get that in echelon form, can you imagine there might be some possibility of round-off error after doing so many row operations? Do you think the round-off error would kind of build if you do a lot of row operations? What do you think? I mean, so what I'm trying to say is the computer uses a lot of decimals of accuracy. Sure, it uses a lot of significant digits, maybe like, I don't know, maybe 10, or maybe a little more, but probably more. But the point is, if you have a huge matrix and you're doing row operations, do you think a very small error in the beginning, a round off error? Do you think with a big matrix and a lot of row operations that a very small error could kind of grow as you do more and more row operations for like a very big matrix? Yes, yes, and that's what I'm saying. So thank you, Eleanor. Thank you, Hung. So the idea here is that they had a little example with just four significant digits, but you can see where even with more significant digits, like in a computer, you have to guard against round off error because you're as computer scientists, as scientists, you're going to be dealing with very large matrices, and even a little round off error if it's in the trillionths place, in the beginning, it could build as those row operations continue. Okay, are there any questions on that? Was this example helpful to help you understand partial pivoting? Was this example good? Shivani thinks so. Thank you, Shivani. Thank you, Hung. Thank you, Benjamin. Excellent, excellent. Okay, so I always like to try to give reasons for when we do things. I mean, I think it helps to understand the reason why we do things. And that goes in math too. Okay, if there are no questions then, are there any questions before I stop the recording? Okay, I'll stop the recording.